Hello all, welcome to the next session of interference. So far we have discussed the analytical treatment of interference fringes, then the Young's double slit experiment. Now we are moving on to the topic interference in thin films. So we all are familiar with the brilliant colors exhibited by a thin oil film spread on the surface of water or also by a soap bubble. So when a thin film of a soap bubble or oil on water is exposed to an extended source of white light is observed under reflected system or reflected light, brilliant colors are observed. These colors are due to interference between light waves reflected from the top and bottom surface of the thin films. Interference in this case of these thin films can be due to reflected light or transmitted light. So when white light is incident on a thin film, the film appears colored and this color depends upon the thickness of the film and also the angle of the light. Now let's see how interference is happening in thin films under reflected system. For this, we are considering a transparent thin film of uniform thickness T and the refractive index is mu bounded by two plane surface K and K prime. You can see in this picture the thin film is formed between the plane surfaces K and K prime, and a ray of monochromatic light AB is incident on the surface K of the film. This will get partly reflected along BC and partly refracted to the film along BD. You can see in this picture. And at the point D, the point D is at the surface K prime. The ray of light is partly reflected along DE and partly transmitted out of the film along DG. And the reflected light then emerges into the air through EF. You can see in this green arrow. And this EF is parallel to BC. So both the reflected lights are parallel to each other. And the ray reaching at EH after refraction at H, it finally emerges along HJ. So to find out the interference conditions, we first we draw a normal from E to BC. That is, this normal is EB. We are drawing a perpendicular line from E to BC, so that the perpendicular is EM. And it's clear that the rays traveling from BC and EF undergoes path difference, and this path difference between the rays BC and EF can be written as BD plus DE, which is inside the film, minus BM in the air. And but we know that the distance in the air is numerically equal to mu times the distance in the medium, which itself is the definition of refractive index. So we can rewrite this equation as the path difference delta is mu times BD plus DE minus BM. And you see in this figure that BD is, this line BD is equal to DE. So therefore we can rewrite this equation again as 2 mu times BD minus BM. Now we have to find out the magnitude of BD and BM. For this, we consider the triangle BME. So this is the triangle BME. Here the sine of the angle of incidence sin I is BM by BE, or BM is BE sin I. Or we can write BE into mu times sin R, since mu is sin I by sin R is the Snell's law. And now consider another triangle BDL. Here you can see another triangle BDL. So here sine of the angle of refraction is sin R is BL by BD, which is half times BE by BD. So BL is half times this line. BL is half times BE. So 1 by 2 BE divided by BD. So BE can be written as 2 times BD sin R. So we substitute the equation of BE in the equation for BM. So we can write BM as mu times BE sin R, which will become mu times 2 BD sin square R. I think it's very clear now. And so the delta, the equation for the path difference was 2 mu times BD minus BM. So substitute again back for the value of BD and BM. We will write 2 mu times BD minus BM was 2 mu into 2 BD sin square R. This will become 2 mu BD into 1 minus sin square R, which will become cos square R. And again consider this triangle BDL. Cos R will become DL by BD. So what is DL? DL is the thickness between the plane surface or thickness of the air film. So this will become T by BD. So we substitute again delta 2 mu into cos square R is T by BD. So this will become 2 mu T cos R. So this is the expression for the path difference for the rays undergoing reflection due to interference or the interference due to the reflected beam. And if a ray of light traveling in the air and getting reflected at the surface of a denser medium undergoes an automatic phase change of pi or an additional path difference of lambda by 2. Also, since the reflection at B at the surface of a denser medium, therefore additional path difference will be of lambda by 2 will be added to the equation for the path difference. So the effective path difference will be 2 mu t cos r plus lambda by 2. Now let's see what is the condition for bright and dark fringes. We know that for the constructive interference, otherwise the film to appear as bright, the path difference will be delta is equal to n lambda. So 2 mu t cos r plus lambda by 2, which is the effective path difference, is equal to n lambda, or for the film to appear as bright, 2 mu t cos r equal to 2n minus 1 lambda by 2. So it should be very careful that in the case of a Young's double slit experiment, the equation was the path difference was equal to n lambda for the case of bright film. So here, due to the addition of additional path difference lambda by 2, the expression will become 2 mu t cos r is equal to 2n minus 1 lambda by 2 is for bright fringes. And for the destructive interference, the path difference is 2n plus 1 lambda by 2 for the thin film to appear as dark. So if you rewrite, the equation will become 2 mu t cos r is equal to n lambda for dark fringes. So you should not get confused with the bright and condition for bright and dark fringes. For the bright fringe, it is 2 mu t cos r is equal to 2n minus 1 lambda by 2. And for dark fringe, it is 2 mu t cos r is equal to n lambda. And suppose if the incident light is incident normally, that is at I is equal to 0, and hence the reflect R will be 0. So the condition for bright fringe will become 2 mu t cos r. For R will be 0. This will become 2 mu t is equal to n minus 1 lambda by 2. And for dark fringe, it will be 2 mu t. This is the condition for normal incidence. So far it's we have seen that these colors in thin films is occurring due to the interference and under reflected system. So now we move on to the classification of these fringes exhibited by thin films. So the thin film fringes are classified into three types. One is the fringes of equal inclination, which is also called Heidegger fringes, and fringes of equal thickness, which is also called Fizeau fringes, and fringes of equal chromatic order. Now let's see each one. The fringes of equal inclination, which is also called Heidinger fringes. So in this case, the thin film's mu t remains constant, and therefore the formation of maxima and minima depends on the value of r. And these fringes were first observed by Heidinger, and hence it is known as the Heidinger fringes or the frequency of equal inclination. For equal inclination, mu t remains constant. And examples are the circular fringes in Michelson interferometer. Is one of the prominent example for Heidinger fringes. And Vizio fringes, if you see, the fringes is of equal thickness. In this case, r and lambda remains constant. The angle of refraction r and the wavelength remains constant. Then the value of path difference depends on the optical path mu t. Such fringes are called fringes of equal thickness. And some of the examples include the Newton's rings or the wedge-shaped films, etc. And the third category is the fringes of equal chromatic order. In this case, mu t and r are constant, and each fringe corresponds to a particular wavelength lambda, and a color pattern of fringes will be observed. These are called fringes of equal chromatic order. So you should remember, for Heidinger fringes, mu t will be constant, optical path will be constant, and for the equal thickness, in the case of Vizio fringes, r and lambda will be constant, and for equal chromatic order fringes, optical path and r, otherwise mu t and r will be constant, and the fringe will be responds to the particular wavelength. So that's all for today. Thank you.